before the test, let's continue with the classical teaching thing. So suppose we have in a LAN 2 or more routers which connect that LAN to other networks. The broadcast stuff only works inside that network. And it works in a way that deals with the IP addressing. And we don't know yet, we didn't study yet how this stuff is implemented, but I'll give you some examples. This is all you need to know from the programming point of view. From the technological point of view, we will learn it a bit later, but from the programming point of view, you only need to know that, for example, if you have a network that has this structure, 0.0, let's say 5, and you have a mask. There is always a mask with any network address, 255.255.255.0. And if I am to show you an example, you find it on Windows, so that you have a practical, in fact, change adapter options to move all these windows here. For example, my Wi-Fi connection status, it will give you this thing and details. You will get the information that you get with the ipconfig command. And you have the IP address. This is the IP address I have. This is the mask. Now, how do you compute the mask? How do you compute the broadcast address for this network? I have 192.168.0 point something, and this is the mask. It's the exact example that I gave you here. Or on Linux, ipconfig will actually, ifconfig or IP address will show you the same info. You have the network address and you have the mask as always there. So with an example like this, what you do is that you take all the bits that are set to 1 in the mask. If you take a look here, there are 8 ones here, 255, 8 ones, 8 ones, 8 ones here, and there is 0 ones here in this part. So all the parts from the IP address which are covered by ones, they stay like that. Okay, so in our case, this one here, this one here, and this one here. Whatever is not covered by the mask, it's 0. You just put the maximum value. You put a 1 everywhere there. So you replace everything that is 0 in the mask with a 1 and combine it with the IP address, and you get something like 192.168.0.255. You might get something like 10 point, like IP address. Okay, let's take another example. Take 0.5.3.9/255. You might get those sorts of addresses at home as well. Well, in this case, the broadcast, can somebody tell me what it will be? It will be 10. That's the only part that is covered by the mask. And then the rest of it will be like this. Okay, that's the broadcast address. So if you want a more mathematical rule, you take the IP address. Let's say algorithmic implementation. You AND it. Let's put an AND with a mask, and then the result you OR it with not mask. And this is basically the broadcast. Okay, so then you go and you take the result and you OR it with the mask, with a negated mask. And you get the broadcast address. Any questions on this? Let me erase all this stuff. And with this being said, we are going to jump ahead. I have some stuff that I need to show you on network diagnose, and we will need to cover some small parts. We start studying the theoretical parts of TCP/IP. Right now it's just an introductory lecture, but next time we will be delving deep into TCP/IP, starting with the IP addressing schema, and there you will learn how IP addresses are made up, how are they used, how are packets routed from one machine to another through internet, and so on. So before starting this, I just want you to remember that during the labs we had to implement problems like this one, for example. Let's take this one. We have a problem where we need to implement a client-server architecture where the client sends an integer number and an array of n float followed by an array of n float values, which the server will merge from all clients and until it gets an array of empty float, and then the server returns to each client the size of the merge sort array. So another number followed by the merge sorted arrays from all the clients. Basically, this is the textual descriptor of the problem. But in practice, what you would do when trying to actually implement that problem, it will be to design something that we call a protocol. And what is a protocol? What is a protocol from our, I don't know, general knowledge, from our general lives? When we're talking a hospital protocol, because we are talking a lot these days about hospital protocols, what happens when you enter into a hospital, what you are required to do nowadays when you go into a hospital.
A general set of rules.
General set of rules that one should follow strictly in order for something to happen. Now, in computer networks, a protocol, it's exactly the same thing. In our case, because we are talking communication, it's an agreement about communication. It's a set of rules that allows two applications to communicate with each other. When they follow, we say that when two applications or more applications are following the same protocol, they will be able to understand each other. And each problem that we formulate textually thing that we formulate textually and that we need to implement or solve using networking, it will materialize in one or multiple protocols that should be followed by those applications that we are going to implement. And what does it specify? Well, a protocol, and keep this in mind, and basically you did that. You did this for all the problems that we have during the labs, but maybe because there were kind of simple problems, not too complex, you did that in your mind. I mean, you did those agreements in your mind. You said, okay, now if I need to send one integer number followed by an array of floats, you already you already created some rules in your mind, telling or fixing yourself on the fact that the integer will be on 4 bytes, that it will be signed or unsigned, depending on how you actually design that protocol, and that the floats will take 4 or 8 bytes. So the format of the messages, what each message is going to be like, or what its structure would be. In our case, from the problem before, you'll have one integer, that's one message, and another message is a string of floats. But the problem didn't say if the floats or the integer should be on 4 or on 8 bytes. So we didn't have to land on it. But the format of the message should contain the representation and the length. Okay, usually you take here the representation plus length. You should specify both these items when you design your protocol. The meaning of the messages, well, that actually comes directly from the formulation of the problem, and you will know how to put there usually. The rules of exchange. That means the protocol should describe what is the sequencing of messages. What is the order of the message in which messages are exchanged between the client and the server? Would, for example, when designing a protocol, you will need to tell when a client connects, for example, in this case, as we saw before, when a client connects, is it welcomed with some sort of message giving it some information, or it goes directly with the client sending an integer number to the server specifying how many floats it will send. Okay, so the rules of sequencing the messages will actually tell in the first step who be addressing to who at first, because if both are starting reading, we saw last time that comes out badly with deadlock, and in which order they talk to each other. Procedures for handling errors. Now this is something that you might have skipped during your first implementations, but a protocol should actually handle at least the important situations that could happen during your implementation. For example, what is happening for the problem that we just specified before? In this case, if you have a number of clients connecting to the server, they all start sending arrays of numbers, but you don't have any of those clients sending an empty array. What does the server in that case? Will just wait indefinitely, stop at some point and return something to the client, stop and not return anything to the client? That's something that you need to put out somewhere in your protocol. What happens if a client connects? It tells you that it is going to send you 20 numbers, and after sending 10 of them, I mean, you get a broken connection. All this stuff needs to be handled. These were just examples from the problem above, but you can figure out there are many cases that you need to handle, and a protocol should cover most of these situations so that somebody, when it reads your protocol, the protocol is the transcription of the textual problem into a set of rules that are, if you want, a formal shape of your textual problem, something that a programmer can look up to and can implement in order to actually solve the communication problem. Those are the basic thing that you need to at least specify in a protocol: the format of the messages, representation plus length, the meaning of the messages, the rules of exchange, and the procedures for handling errors. If you cover at least these 4 items, then you can consider that you have yourself a protocol there. And actually, you need to design the protocols like this every time you take up a problem and you try to solve it. This is the first step you need to do if you want your thing to be properly approached. Now, for very simple problems, as I did, you probably did that in your head. You established for a given problem that the numbers will be exchanged into binary representation and in big endian format. That's obvious, but you also has in the rules the length, or you also thought you were still thinking what will be the length of those numerical representation and such stuff like that. Okay, so the textual problem equals a protocol design all the times before programming anything. Whenever the problem that you're going to implement it's a little bit more complex than a problem written in 2 or 3 lines of code. Sorry, 2 or 3 lines of text. Why do we need protocols? Well, we need protocols for various reasons. The labs that we just had weren't very good examples for why we need would we need protocols, because they were not complex enough. Most of you could represent those protocols in your mind, and you didn't feel the need to actually write it down. But if we approach all the 4 items that need to be specified during the protocols, I'm pretty sure that you didn't think of all error situations that you needed to handle, for example, for any of those problems. So we need protocols because the first reason, hardware is low level, and because hardware is low level, we can expect various situations that can happen. And even though we think that the socket interface is kind of low level itself at this point, in fact, the socket implementation is pretty high level compared to what hardware is actually capable to do. On the hardware side, things are even most simpler, and you need to assemble multiple bricks to do, for example, a simple send operations. At the hardware level, there are various things, an entire sequence of things that is happening when you're sending something. You need protocols because there are various problems that can occur. And those are failure to communicate, not enough memory on the client side, not enough memory on the server side, chunks too big chunks of data that need to be sent, and problems because of that, and different representations of data on different platform architectures, and so on. What can happen? Well, other examples are, for example, something that they didn't mention before is that during transit, bit of data on the wire or on the wireless, encoded as a wireless signal if you're working wirelessly, could be corrupted or destroyed. For example, if you have a cable network that goes near an electric engine, whenever that engine gets spinning up, starts spinning up or spinning down or things like that, or accelerating, it will induce a magnetic field around it. It might penetrate your cable shield, and it will definitely, if that happens, it will definitely alter the electrical signal that passes through the cable, which encodes your actual data. What happens in those situations, it's either bits get corrupted, and by corrupted, it means most of the time flipped. You have a number represented like 0, 1, 1, 0, and it gets, after being corrupted, to 1, 0, 1, 0. And that's a problem that we need to handle. I mean, usually it's not us handling that, it's the networking layer, but somebody designed some piece of software that actually deals with that. Entire packets could be lost. Yeah, that's another situation. That's mostly because when sending a packet through internet, it passes through various routers that are passing information from one network to another. And at some point in time, for example, one of those routers are overwhelmed by the quantity of data, of packets that they receive at a given point in time. So they might choose to throw away a few packets. And one of those is yours, and that problems need to be handled. Packets could be duplicated. Yeah, that's a very strange problem. That could happen. In reality, it usually doesn't happen in a local area network as it is, but as you go through multiple routers on internet, that could happen. You could have a packet that gets duplicated in some way, and it arrives at the destination duplicated. And with UDP, that can happen in reality for you. And packets could get delivered out of order. That's not going to happen as well in a local area network, because in a local area network, you don't go over any routers. But as you go out on internet, different packets between, for example, if we take a LAN here, let's take a machine, just it will be simpler. A connected to some sort of internet, large internet. And suppose we get out at the other end of an internet in another network, we have a bunch of routers in internet that specify various, the drawing that I had a few times already during this class. And we have some different paths from that could be taken by packets. In this case, we could have one packet one, traveling this way. Packet one, it reaches a destination, then we can have a different packet taking another path through internet. For example, this one, packet 2, packet 2, packet 2, packet 2, packet 2 here. And it might happen that packet 2 arrives earlier than packet 1 at the destination, either with UDP or with TCP behind. There are IP packets at all times. So what happens when they get delivered out of order? That's another thing that needs to be specified for each protocol. And of course, there is flow control. A protocol should handle or should specify that it doesn't handle any flow control. What happens with the amount of data you can inject per unit of time into the network and send to the other side? And we are talking here about protocols from the communication protocols point of view. I mean, we are at the TCP IP level, and we are which is a protocol by itself. So TCP/IP, for example, either TCP, UDP, and IP will have or will be defined over a set of rules that handle all these problems, in fact. And flow control is a thing that tells you how data should be dispatched with what and with what speeds. Do I handle the fact that the other side is not able to cope with the amount of data I'm sending it or not? TCP does that, for example. UDP doesn't do that. So it's a choice that has been made. TCP handles flow control. UDP doesn't handle flow control. Okay, let's take the break now, and okay, so I'm back. We can just confirm if we can move on and continue with the lecture. I'll try to speed things a little bit because we need to cover a lot of stuff in the remaining time. So just tell me if you're okay. Everyone is back. We can move on.
I guess so, yeah.
Yeah.
Yes, we can.
Okay, so we saw this part, and the conclusion that we already discussed is actually that, sorry, it's actually that basically every time you implement your lab problem, you actually design a protocol formed out of specific rules that will govern the communication. And then usually your implementation in your protocol is designed on top of TCP or UDP, because these are the two protocols from the TCP IP that you can actually use programmatically. Okay, this was about protocols. So probably next time, if the problem is a little bit complex, then take 10 minutes to actually design your protocol before going directly to the implementation, so that you don't miss things that are required by the problem textual representation, and you fail to solve completely the problem. Now, let's move on. And we will need to see shortly in the following 10 minutes another thing about networking communication. And let's look at this point in time only at the superior part of this slide. And let's think we have two philosophers. One, a Hindu philosopher probably in Asia somewhere. And let's say we have another French philosopher in Europe, in France, for example. And let's think that they try to talk to each other. We don't care right now about how do they talk to each other, but let's think they want to talk to each other. None of them knows the other. The Hindu philosopher doesn't know French, and the French philosopher obviously doesn't know Hindi. Well, because they are why? Because they are actually more focused on their own philosophy and studying philosophy and things related to philosophy, they kind of neglected talking foreign languages, which is a problem for them right now. How would we handle that? Well, luckily, it seems like each one of them could hire a translator. And if they find a translator that has a common language, I mean, if the two translators found have a common language with each other, well, then problem gets a little bit easier. For example, in this slide here, we have two translators that both speak Dutch and both speak respectively Hindi and French. So for the Hindu philosopher, the messages that he's giving in Hindi, they will be translated into Dutch by the translator, and the French messages will be translated into Dutch as well. And we get here a new layer, a new service that actually takes the raw data, I mean the usual data that the two of them needs to transfer, that's the message or the conversation that they're having, and they're translating it into a common language. And well, the translators, that's all that they can do usually. They don't do other stuff. So they need help from a different service. And luckily, both philosophers have some sort of secretaries that know to handle some sort of communication medium. We are in some, let's say, somewhere 10 years ago or 15 years ago, where fax is what highly rated, and all these two secretaries can do is, I mean, a version of what can do is that they can take the written message in Dutch and typing it or putting it into a fax machine and encoding it into some sort of, let's say, sound signals that are sent over a communication line, in this case, a telephone line, recovered on the other side, translated back into some sort of written message in Dutch, and then passed over to the second philosopher. For example, that's written Dutch message, it's passed to the translator, which takes it from Dutch and gives it to the second philosopher. Why did I go and take the effort to explain you this very simple thing that is obvious to anyone? Because this is the way things are happening with networking. We have various types of needs in communication that are handled with this kind of layered, modular, layered architecture, where we have different layers implementing different services, exactly like in this approach here. This one is very simple. We have 3 layers: philosophers, translators, and secretaries. But in real life, with TCP, this is used as well. We'll see that the number of layers is different. I hope this example could be an image of why that is happening in networking in this way. We have here, like you see, a medium, let's say a medium for transferring data. We have some sort of transformations on that data, and we have the actual messages encoded at the high level, which suffer different transformation in transit between the two communicating parties. Exactly the same thing happens with with communication protocols, and networks are organized exactly the same way as a stack of layers in order to reduce complexity and in order to isolate the type of service that each component gives to components that are linked to it. Exactly like in a, let's say, because you did object-oriented programming, exactly, I mean, or similar to the way things are taken upon in an object-oriented way with encapsulation. You have a service encapsulated in some sort of class definition, and then you have an interface with the exterior. And there are other components or objects that are linking to your object by means of messages. And by doing that, they kind of exchange data. So it's some sort, it's equivalent to data abstraction. And the network architecture is a set of layers and protocols. We have an example here with a 5-layer that goes on top of some physical medium for data transmission. By physical medium, I understand, for example, it could be an electrical signal, it could be a waveform, it could be some light signal, it could be some encoding using fire and smoke, whatever you think of. It could be anything. And there is a standard which is called in networking, and this is the thing that I need you to remember from all this story. Let me just, okay, to go to pen. I want to choose this. The open system interconnection model. Open system interconnection reference model, or the OSI reference model, is the one that all networking protocols use to actually define different levels of service. And you have 7 layers into these reference models that most communication protocols are mapped to. In order to easily, there are application, presentation from top to bottom, session, transport, network, data link, and physical. And as you go higher, you are higher level. As you go downwards into the reference model, you have you go from higher level to lower level in whatever that service means. If you want to know and to remember all these layers, because you will need to know this all, as I told you, all that you're going to, not only limited to this class, everything that you are going to study about networking, communication protocols, they will be mapped into some way into this reference model. There is a power phrase that you can use in order to remember all these layers. All people seem to need data processing, and you take the first character of each word, and you get them from top to bottom. You get all the layers, all application, presentation, session, transport, network, data link, and physical. Now, these are the 7 layers. How was this model designed? Well, it was designed with a few ideas in mind, and I'll go fast over it because this is mostly philosophy. A layer was created wherever a different abstraction was needed. Well, another idea was that each layer should perform a well-defined function. And we don't need to have functions that are too complex on their own and perform operations at different, if you want, levels of abstraction. The function of each layer should be chosen with a start that's with an eye towards internationally standardized protocols. The layer between boundaries should be chosen in order to minimize the traffic flow, the data flow across interfaces, and number of layers should be large enough so that distinct functions need not be thrown together in the same layer just because we don't have enough layers. Well, this was the philosophy behind it. I don't need you to actually remember this, but I need to remember that there is this model. And now, very shortly, what does each of those layers do? And if we take it from bottom to up, there is the physical layer. It's the most basic unit of service. What it handles raw bits communication over a communication channel. Okay, raw bits transmission. You take bits of data. How would you send it over a communication channel? Or how do they how is a bit mapped to some sort of signal? If we take how like a signal, how do you represent a 1, how do you represent a 0? And if it's an electrical signal, for example, an electrical signal usually goes as a function, a sinusoidal function that goes like that. How do we encode once it's 0? For example, we can say everything that it peaks, it's a 1, everything that it's a valley, it's a 0. And then we count the peaks and the valleys, and we have our signal. But then there is a problem for an electrical encoded signal. Of how many volts do we take for a 1? How many volts do we take, for example, for a 0? How much time, if this is the time and this is the amplitude, how much time do we need to maintain the voltage at a given layer, at a given level, sorry, in order to say, okay, this is definitely a 1? How do we handle bidirectional simultaneous transmission? What are the electrical, mechanical, or timing interface? I'm also talking mechanical because you can think of at this physical layer, you can think of encoding the signal, the encoding data as a sound, for example. You hit a surface with a hammer, and every hit is a 1, every pause is a 0, or something like that. You can think of anything you want as a transmission media here. And feel free to ask questions, okay? If you have any questions, these are not complicated things, but we'll start studying IP addressing, I hope, this very class. So the data link layer, it's above that physical layer, and it turns the raw transmission, the encoding of that bit into some sort of other types of signals, into an error-free communication line. At the physical layer, you had some sort of signal, which is kind of continuous in time. At the data link layer, we take that signal, which we had before, something like this, and we turn it into some sort of individual units, which are called frames. If this is Wi-Fi, again, you have some sort of wave, which is divided at some point in time into chunks, which are called at the data link layer frames. And is the first layer that turns the raw transmission into an error-free communication line. Error-free not from the point of not having errors at all, but having errors which are dealt with. And typically a frame, it's a number of thousands of bytes. It also handles, at this layer, we also handle traffic regulation or flow control. We are able to control here how much data we send, how much data we are able to actually receive at any point in time. And this is the point where we actually we implement a service is implemented. Basically, what is happening into a cabled network is that your data is encoded as an electrical signal that travels through the wires, and it gets then it gets represented as a frame here at the data link layer. And a frame contains some sort of header and some sort of payload. And you'll see that this is happening at every other layer. In the header, you have something which is source MAC address, destination MAC address, and a bunch of other stuff. And in the payload, you have the actual data. Now, if we are to take an example of what MAC addresses are, ipconfig. I see that ifconfig works in this one as well. So on Windows, this are the things that we are calling MAC addresses. These are some addresses represented on 6 bytes, as you can see here, that uniquely identify a network card. We will see on this later on. Each network card manufacturer has a range of into this 6-byte address space, and it takes out from that range with each network card, with each Wi-Fi network card, with each cable network card, it takes from that range and it assigns a unique MAC address from that range to every network card. And this is the basic of communications. At the data link layer, we have always some sorts of addresses which are pre-burned, are burned into the network card, and they help identify a network card inside the local area network. Then we have the network layer. This one controls the operation in a subnet. We will see this is the level where the IP protocol actually happens. IP protocol goes there. I will see that later. And in fact, it deals with, it divides the communication into individual islands called networks, which are interconnected to each other, for example, by routers. This is the first layer where we can talk structure. We have a network that has a structure, and we have different local area networks. 1, 3. At this point on. And this is the layer that actually defines how packets are directed from a source to a destination machine. It handles quality of service, but we'll see that later on, and fragmentation and inter-network problems. What happens, for example, when a chunk of data traveling from here to here, this way, it's too large to pass over. Think of it as a parallel from the real life. This is a bridge that we need to cross. And we come here with a very large truck, which doesn't fit the bridge. Well, in real life, you don't have any solution to that. If the truck reaches that bridge, well, it needs to turn back and take a different path. We will see that in network communications, sometimes it is possible to split that very large truck into smaller trucks, smaller packets that traverse that, and they go to the destination. The transport layer is where the actual TCP and UDP are implemented. It takes data from the upper layers and splits it into smaller units, either segment, and we are talking about, at this level, we are talking about segments. On UDP, we are talking about datagrams here, the unit of transfer, or packets. And ensure that those transmission units arrive correctly to the other end. Now, TCP ensures that, UDP ensures that we will see that they arrive with some parts of it unharmed, and it doesn't care about some other parts. And it also, at this layer that is defined, what type of service do we have? Do we have an error-free point-to-point? Do we preserve order or not? Do we have guarantee on delivery, and so on and so on? This is the true end-to-end layer. If we're going back to this, as you can see, up to this point, we have some sort of internal stuff here. The transport layer is the first one where we think that in an abstract way, the transport layer on machine A talks directly to the transport A to the machine B. Then we have the session layer. Well, this is a layer that has been defined in order to define what a session is. What is, how do we define a communication where we start the session, we maintain, and we tear it down at some point in time. This is something related to establishing and tearing down sessions. Synchronization. The presentation layer, it's something that handles data representation. How is data encoding on the wire? How do we actually present different types of data to the networking protocols? And the application is the one that actually implements a lot of protocols, and applications. For example, at these layers, we define the protocol and the rules handling or dealing with HTTP. How do you browse the network with a network browser? Well, HTTP protocol manages that. How do we do file exchange over the internet? Well, FTP protocol handles that. How do we do remote command executions from one machine to another? Well, SSH handles that. How to exchange email? SMTP, which stands for Simple Mail Transfer Protocol, handles that. And this, we reached the last one. And now, if we take a look at how the TCP reference, TCP IP is here, reference model gets mapped to the actual open system interconnection model, well, we get this first layer from the open system reference model mapped to a layer which is called application on TCP. Then the transport layer, it's a direct one-to-one mapping into the OSI model, OSI model. So it defines exactly the same types of things as specified by the reference model. Then we have the internet layer, which gets mapped directly to the network layer into the open system reference model. And we have something called the link layer into the TCP IP that gets mapped to these two, to an ensemble of these two layers into the open system interconnection model. So the link layer in TCP will handle both splitting data into frames, ensuring an error-free communication channel, and data digital to some sort of analog signal. If we're talking about electrical signal, if you're talking about wave, if you're talking about light. So TCP has chosen to implement, as you can see here, 2 layers in one and 3 layers in one at the top, and it only has 4 layers in total. But for TCP, this is enough. It still maps all together on all the layers on the open system interconnection reference model, as all protocols will do from now on. And this is the way it looks like. And from this point on, from this day on, we are going to start studying the TCP/IP protocol at all these layers. We will see how is the protocol implemented and what it implements at the link layer, internet layer, transport, and application. We will see less about the application, because at the application layer, in fact, it's something which is defined inside TCP/IP, but it's already an application. HTTP is not something which is part of TCP/IP. It's a different application that works on top of TCP/IP, yet it's at the application layer. SSH the same, SMTP the same. Whatever you design during the labs, it's something that your labs are going here. It's a protocol that you designed and you put into the application layer of TCP/IP. It consumes services from the transport layer, and it works there. Now the same mapping presented here, and not that important. And on the 4 layer of TCP, we have some sort of examples of what is implemented where. For example, this is a service that does remote command execution, not used nowadays, but you could be using it to test your things. It can connect over TCP to any port, listening on any server, and then you can type in directly from the keyboard data to be sent to the other side, and whatever is received is displayed on the standard output. This is file transfer protocol. File transfer. Okay, implemented application layer. This is mail. And this is something that we approached briefly. It handles IP to name to IP address conversions. Okay, so what it does, it takes a name like www.cs.ubbcluj.ro and gives you back an IP address, or it takes an IP address and gives you back possible names for that IP address. At the transport layer, we have the TCP and UDP, the two protocols, which are serving these, or these are using the transport layer protocols, which in turn are using services from the IP protocol, which is implemented lower at the network level. And the IP, actually, it's using a bunch of other stuff from the physical link or link layer. And those things are dealing with how data is actually encoded in transit. ARPANET is some sort of physical layer protocol. SATNET is something that goes over satellite. Okay, your data, it's encoded in some sort of way, which gets delivered to some geostationary, normally satellite above the Earth, which that goes something like that. You have some sort of network of satellites above the Earth. You get your signal there. It goes over from satellite to satellite and goes back, bounces back on Earth at a different location, and gets delivered locally as data. No? Packet radio, it's Wi-Fi, GSM, and stuff like that. LAN, it's a different technology working with cable network and stuff like that usually. Okay. There are a bunch of standards that actually defining all that we are talking. Every protocol is described in some sort of standard documentation, and there are some organisms that are actually handling these things. In Europe, this International Telecommunication Union is the organization that defines how each protocol should be made on, and it describes that in a series of documents. And those documents, IEEE, you've heard about IEEE, I'm sure. There are lots of conferences held by IEEE, Institute of Electrical and Electronic Engineers. They are managing not only development into the computer networking, but in various fields related to IT and to electronics and electrical things and stuff like that. And they're holding a lot of research conferences where people are presenting their research, and they're helping the entire research on that topic to move on, to gather new things. And the standards that I told you about are some sort of documents where you can pick up. They are freely available normally, and they have some sorts in computer networking. They have some sorts of numberings like that. For example, the protocol, the document describing the overview and architecture of local area networks is described by a document called by a standard called 802.1. Ethernet, which is cable network, 802.3, and whatever. This one, I'm pretty sure you saw it in practice on your router, because it's really called like that, defined as that as protocol on your router, 802.11, and so on. This is Bluetooth. These are standards for communication, and these are actually defined in some sorts of document. Discard some sorts of documents that are maintained by rfceditor.org. Okay, if you go into this site or itf.org/rfc, if it's still, yes, you have here all the documents And this time they are represented as because all those standards that I told you about are not written at once by somebody and they are given to everyone. These are actually advancing as research on that topic goes on a number of years. And they are materializing at first by something which is called request for comments. For example, I design a new protocol, I submit it to a conference or to IEEE, and I tell them, this is what I was thinking about, a new way of transferring data faster over fiber optics. And request for comment says, okay, let the community, research community, look at it and bring back comments on what I've done. The document is evolved by the entire research community. And at some point in time, it reaches some level of maturity, and it gets translated into a final document, still called request for comments. By the end, the name it's kept because it might evolve in time, even afterwards. For example, 10 years after it gets stable into a stable phase, somebody might add something to it. And those documents are the stuff that you are actually getting on those. Sorry. Those documents are the stuff that you are finding on those sites I told you, RFC editor or IETF.org. Every protocol is described by a series of requests for comment documents like this: RFC 775, RFC 9959, and whatever. You find them. Here. RFC editor. You can search, for example, HTTP. And you find all the documents related to HTTP. For example, the Hypertext Transfer Protocol, basic, is described in request for comments 1945. You can get a ASCII copy, a PDF copy, or an HTML copy of it. And it looks something like this. It's a document that it's held on 60 pages here. And you get the description of HTTP 1.0, the actual protocol. Okay, now, whenever you need to look up on some protocol related to any networking, you go and fetch the documentation for it on this request for comments. This is actual protocol, so it's kind of made for something somebody which is not only programming aware but computer science aware. So they are not written into some novel style, way. They are actual technical documents. And let's stop here with this presentation. I don't need to save this, and let's move on to some new part. Okay, and with this, we're stopping with the standardization. Okay, so keep in mind from the previous lecture that there is a standard. The standard reference model for anything networking is the OSI model, OSI model, and it's composed of 7 layers: application, presentation, session, transport, network, data link, and physical. And from this point on here, from this lecture on here, we are going to study, we are going to start studying from the prism of TCP, this one, the network layer, because this is where the IP protocol is implemented, and it's the lower level protocol into the TCP/IP stack. Whatever below it handles, as I told you, data link. I mean, the physical link and the data link, which are kind of common to all communication protocols. We are going to study later on, by the end of the semester, those shortly. But IP is already specific to the TCP/IP protocol, and we are going to study this. We are going to move up this way, and then we are going to study at the end this part. And with this in mind, we are actually studying the IP protocol. What are the services provided by this layer? Well, the IP protocol defines the IP addressing, and this is what we are going to start with if we manage right now, but probably I will leave it for the next time because we only have 10 minutes. How a datagram moves from source to destination. This is also defined at the IP layer. What's the datagram format? How do we, divide those large tracks into smaller tracks whenever that is possible? Tracks transporting data, so packets. What happens when some sort of communication line doesn't handle a very large packet? What do we do with it? Some sort of diagnose messaging over the internet and some various protocols at that low layer. For example, DHCP is the protocol that allows you to dispatch, to give IP addresses dynamically to host inside the local area network. We are going to also, define some other types of services, and this one is actually related to moving a datagram from source to destination. That process is called routing, and we are going to study all these in the following classes. And in order to start, the common thing at the basis of the IP protocol is the IP addressing. And now can somebody tell me everything that you know about IP addresses? What are they? What are they needed for? And are they plugged into what you've seen up until now during computer networks? Because you've been using IP addresses for at least 5 labs already. So that's at least 10 hours if you only count the time that we spent for the labs. Anyone? What is an IP address? You have it also on the slide, but that's only partial information.
Well, it's an address on 4 bytes, so kind of a number, I guess.
It's a number, exactly. And it helps us to do what?
Identify computers in a network.
Identify computers in the network. Why do we need to identify a computer in a network?
To know where we send information so that we can communicate between computers.
To help us communicate between computers. Okay, and yes, basically it's a 32-bit entity. In IPv4, it's this. And there are some other protocols where the addresses are not 32 bits, but with IP, you get something like this. Okay, you have an example here. We have here a number of networks. By looking at these networks and a number of computers, by looking at all these computers, can you tell me something about the architecture of the thing which is here? I mean, you don't have necessarily the knowledge for that, but maybe some of you already know. We have a router here. This is a router. Can we tell something about this entire network architecture by looking at all this stuff? What you see if you look at the IP addresses?
They all start with the same 2 bytes.
Yes. They all start with the same 2. Well, yeah, okay. But if we look closely, you have subsets that are starting with the same 3 bytes, in fact. The same 2 is holding as well, but if you look, On this side, they are all starting with the same 3 bytes. On this side, they are all starting with the same 3 bytes. On this side, they are all starting with the same 3 bytes. I should have taken this one as well. Some common prefix here, which tells us something about the structure of the network. Okay, so let's stop here with the idea in mind that the basic, and let's stop here because I want to show you in the remaining 5 minutes something that you can use from your lab. Let's stop by the idea that we need an identifier in order to communicate between computers. That's the IP address. Then we have the thing which is called interface or network interface. That's the connection between a host, router, and the physical link. The network adapter, the network card, is the thing that connects your cable or your Wi-Fi to your computer. And in a typical network, routers typically have multiple interfaces. You can see here, there is one here, there is one here, there is one here. It has 3 network interfaces. That's not always necessary, but it's usually they have more than one. If they don't have more than one, that means that they cannot, they are not bridges to anything. If it's just a network interface towards this network, towards this side, sorry, that bridges doesn't cross anything. It just stays on this side. A bridge from the road point of view, from the transport point of view. Host may have multiple interfaces, but usually they have one. And an IP address at least is associated with each network interface. And let's stop with this idea in mind when we'll continue from this next time. And in the, okay, I didn't want that to stay on. In the remaining, I want to show you something that you can use for your programming part. Not sure if you've remind me later if you've covered this during the lab. If not, maybe all this week. But if you don't, let me show you briefly. There is a tool called Wireshark or TCP dump. Okay, it's TCP dump. It's a tool that allows you. You don't have it by default on Windows, but usually you can install it from packages on any Linux. On Windows, you have this one with a graphical user interface. This is text-only interface. And also you have a tool called Wireshark above it. It's one of them, which uses TCP dump, and it's a graphical user interface. What these things do is that they are able to inspect network traffic. When you launch it, it looks something like this. And because I'm connected to the Wi-Fi network right now, if I double click on this thing, what I can see here is all the IP traffic that my machine is doing over the Wi-Fi connection. You can see here the source IP address and this. I'm not sure if I can make this larger for you. Is there any zoom to this? Yeah, here. Okay. So you see all the packets that my machine, in fact, it listens to all my network adapters, and you see all the traffic. Here, for example, if I go to some website, I should be able to handle this. Right now, the traffic that you are seeing is probably the traffic that Microsoft Teams is using in order to stream the sound session and video session with a video capture of my screen to you. So you see a bunch of packets, all destined to 52.115.132.26, and we can click on some of those packets. It tells you that this is a UDP protocol. As you can see, Microsoft Teams, because we discussed this one lecture ago, 2 lectures ago. For this streaming part is using UDP, as you can see here, and this stuff it's going on and on and on. It scrolls and it scrolls and it scrolls. We can take a look at the structure of this packet. We can see that it's a frame, a physical frame, because we just talked about electrical signals and stuff like that. This is the actual frame coming from the data link layer, or arriving at the data link layer. It has 163 bytes, and converted to some sort of Ethernet. It's Ethernet from the point of view of frame structure, because Ethernet usually it's cabled, but Wi-Fi and both Wi-Fi and Ethernet cables are using in the end the same frame structure. We have a source MAC address, the one of my network card, Wi-Fi network card, and the MAC address of my access point at this layer. And then we have some type which says it transports inside an IP protocol. Then inside that Ethernet frame, we have an IP packet which has a header, which contains, if we look more closely, a source IP address and a destination IP address, the ones that we see here. And it's carrying inside a UDP protocol. And we can unfold that further on, and we see that the UDP packet, it has a source port and a destination port. And it has some land, a checksum, something to learn about. It's used to check the integrity of data. And then finally, we have some payload, which is the actual data that Microsoft yeah, somebody is writing me that don't go on HTTP website with Wireshark open as matters. Not sure, probably you're talking about HTTPS versus HTTP. So my example here was what I was trying to tell you is that we can inspect the traffic and we can actually take a look at the data which is actually transported. If I do an HTTP request right now to a server, but we are during the break right now, so I will try to show you this maybe next time. Although next time it won't be as useful to you. I will actually instruct lab teachers to actually present you this further on. The basic idea is that we can pick up, take a look at all the data in transit. And why is it helpful? At this point on, it's helpful to you if you want to see when you send something, for example, a numerical representation, how does that get transferred, how it's encoded over the wire. When you send something over UDP, an integer, you can take a look inside the payload of that UDP packet. When you send an integer, it will only have 4 bytes, and you can actually see its representation on the wire directly as it gets over to the network card and on the wire. And you can see if something goes wrong with your application implementation, why it does that. Because data is represented, I don't know which way, because the length that comes in a UDP packet is not what you expected and stuff like that. And you can do that over TCP or UDP, and you can actually write filters here. IP point destination. For example, I can filter out that traffic. It's different than 52.115.130.226. It's different. Minus here, okay. Come on that space, why is it so small? Or not IP equals that. Okay, and now we see the traffic that it's not. Okay, so you see some sort of other traffic which is not anymore Microsoft Teams, at least not the streaming part. And with this in mind, you can take a look at everything happening network layer. I see something is somebody, for example, is using some sort of torrent protocol inside the local area network. I'm pretty worried because I know that nobody uses now torrents on my local area network. Okay, with this in mind, I will stop here, leave you to your break. And if you want, before the examination, before the test, we can have a short, I don't know, I can have a short meeting with all of you or with separate groups. Just propose me of any questions, either this week somewhere or next week at the beginning, Monday or Tuesday at latest. Okay. Next Wednesday, be prepared, 8 o'clock. Don't miss this class. You will have the test, the program from the first part of the programming part of the part of the labs. I will stop this. Quit without saving. I will stop this. And stop the recording.